Hello. Hello. Good morning, Daniel. Good morning, Ashley. Good morning. Good morning, Noelia. Sorry, you were the first. Good morning. I said Noelia. Catherine. Good morning. Good morning, Michelle. Good morning, Alyssa. I love this. Good morning, Darina. Good morning, Nikaya. Good morning, Luna. Good morning. Good morning, Yasmin. Good morning, Amarani. Good morning, Amarani. I love it. Okay, who did I say? Michelle. Morning, Michelle. Good morning. Who I think I did. Good morning, Ashley. I'm sorry. Did I say Ashley? Good morning, Ashley. Good morning, whiteboard. Okay, wait. Is that? Sorry. Oh, good morning, Shitlali. Good morning, Luna. Good morning. Good morning, Antonio. Good morning. Okay. Also weirdly, okay, we're going to start in a second. Also weirdly, oh yeah, you can move the squares. Oh, Ed, good morning, Chitlali. Sorry. Yes, good morning. And I just learned yesterday from my 8-year-old. Good morning. Hello, Jennifer. Hello. Cool. I didn't know you can move the squares around. Excuse me, in gallery view. You probably all knew that. I did not know that you can move the squares around. It sort of makes a difference, kind of. Okay, we're about to start. 2 more people coming. Sorry. Okay. Okay. So we're going to start in a second. Again, I think you guys are all very on top of the homework. I think if you just turned in something in the last couple of hours, then I haven't gotten to it yet. But other than that, I think if you turned anything as of last night, I think you got it back. Hopefully, if you haven't, let me know. Who else? Okay, I think we're coming. And we're moving along. Um, and we're going to try a little experiment today. I finally realized, I don't know why I didn't understand how I could. So I'm going to put the board in landscape mode today. It might be better, but if it's worse, I'm hoping it's better. But at the end, let me know. I'll go back to the old way if this doesn't work. Okay. Good morning, Asia. Good morning. Good morning, Jean-Pierre. Good morning, Molly. Okay, I think that's it. Good morning. Good morning. Thank you. Good morning. And that's not okay, cool. All right. And good morning. Yes, good morning. And good morning. Good morning. Thank you. Good morning, both of you. Okay. Cool. Okay. So yeah, I think we can. Again, as always, of course, I'm just going to start rolling to get to the physics faster and faster each time. But it's not to cut off questions. Any questions at all about homework, grades, physics, please stop me. I'd rather be answering questions than just talking, but there is always something to say if I am talking. So in the absence of questions, I'm going to this. Yeah, I'm going to back to where we were yesterday. So on this board, so maybe it's harder to read. Again, I'm going to go this way instead of that way. So it might be, but the 2 equations that you see on the board right now, there are 3 equations that you see on the board right here. Okay, there's just the welcome to today board, but the just to be as clear as possible, the first 2 equations that you see here on the board, in principle, are a summary of what we were saying yesterday. We learned them yesterday, Monday. They are our new equations now. They've tripled our list of equations from 1 to 3 in a way. Okay. But in principle, we established them Monday. I'm going to keep talking about them. I'm going to tell you how to use them. But then the third one there, just to be clear, is sort of a goal for today. If you don't recognize the third one at the bottom, you're not doing anything wrong. We haven't said it yet, not in math terms anyway. So it's sort of what we're going to get to today. But okay, but and all of this is in the context. What we're going to be mostly talking about today, hopefully, is going over homework sheet number 4, average acceleration. As far as I'm concerned, also to summarize, we've gone over number line as far as I'm concerned. We've gone over homework number 2, average speed, as far as I'm concerned. 3 was train of thought. It's not like we went through every single question or something, but we've discussed a lot what the whole point of it was. So as far as I'm concerned, we're done with homework 3. Still, any of you who have not turned in one of those, you can still turn it in. You can still get points. Maybe I might take off some for lateness or something, and I'll tell you if I do, but it wouldn't be enough to not be worth it. You can still turn in any of those 3, but I think we're done discussing. And yeah, they'll be on an exam. We have to talk about exams, but we're done discussing them now as far as I'm concerned. We're moving to homework 4, which is what we're up to. yeah, just to tell you where we at. But also with homework 4, we're going to start talking about it now. That should hopefully be clear to people who have done it. But if you haven't done it, this doesn't mean it's too late to do it. I mean, maybe you want this help, and that's fine. Okay, so it's all about homework 4 and about acceleration today, these kind of new equations. Okay. Again, just stop me if you have any questions, remember. But that being said, oh, sorry. It's here. Sorry, hold on one second. Okay, I'm sort of lying here. I'm saying this is what I'm writing now. And again, just bear with me. I'm trying to make this more like I'm trying a different way of drawing. It may work. Hopefully it's going to be better, more like good old blackboards. But if it doesn't work, just bear with me and you'll let me know. But I'm also lying right now. I'm saying that what I'm writing here is in summary from what we did Monday. Yes, that's true. Like you'll follow what I'm saying now if you were here Monday, but actually I'm trying to take the English of what we did Monday and put it into direct math terms. So I'm actually going to give you new information here, new notation, new symbols. Okay. So really, I'm like, it's not really a summary. It's actually really a next step, but just so, sorry. Again, please bear with me. Sorry, this is. Hold on. Okay. See, that is the problem with this. Sorry. I'm so embarrassed. Okay. And hold on 1 second. Hold on. Wait, no. Sure. No, I just. Oh, no, camera. No, absolutely. Okay. Hold on. Okay, sorry. Okay. Okay, I just want to quickly so what I just wrote here is math. Like strictly speaking, this is my expression of calculus, the calculus that we now is going to start seeping into our physics, or that we're going to need to explain our physics, right? Like you've seen this before in some form, but this is me telling you my version now. This is not me saying, don't you all remember this from calculus? Come on. This is me saying, okay, here's a thing from calculus that may or may not have made sense to you when you learned it in calculus. To be honest, it didn't make sense to me when I learned it in calculus, but if we start using it in physics now, it's not because we're assuming it made sense in calculus. It's because actually by using it in physics, we may see why we ever learned it in calculus, and it might actually make more sense to us. I mean, so please look at whatever calculus we do in physics here or in the next semester. Please look at it with an open mind. Don't look at it as like, oh crap, here comes that thing that I'm supposed to know. Look at it as, oh, here comes something that maybe I'll know better now if I actually get to use it. So what I'm saying here, to summarize from Monday, is that, picture any variable at all you want in the world. Like you could picture X as a variable to measure positions in space, or picture T as a variable to measure moments in time, right? Like we were talking, and whatever variable you're thinking about at all, let's just call it Z for the moment. Like I'm going to use Z when I'm introducing notation here. From here on in physics, Z, yeah, sometimes it means the third dimension or something, but generally Z isn't used very much for any particular thing like T is. So often when we use Z, or at least when I use Z in physics, I mean it to stand for just like any variable you could think of. X, Y, theta, if we're measuring angles later on in physics, or whatever. So Z stands for any variable, okay? If from here on in, you've seen deltas many times in math, like delta Y over delta X, like rise over, right? That kind of delta, you might think delta means change. I want to encourage, so that triangle I'm talking about, right? From Greek, that delta, you might think of as meaning change. I want to say maybe a slightly better way to think of it is as it means difference. Like delta stands for difference. Of course, there's a big similarity between difference and change, but from now on, whenever you see a delta, any variable, think of it as, okay, we're measuring, Z is some variable, some measurement we're making as scientists. And we're measuring, and we're measuring something numerically. It's changing. It changes back and forth. If we pick any two values of that variable, as long as the difference between the two values, it might be small on some scale, but as long as it's still big enough to be finite, right? Delta refers to a small but finite difference between two values of some variable that we're calling Z for the moment. Okay, that's what delta. So whenever you see delta, you mean like as in. I mean, and I am, well, as in. Hold on. Okay, like as in delta y is y2 minus y1 when you're talking about like the difference between two values of the y coordinate on some graph, right? Like that's what delta means. But when we look at the difference between two values, when the two values get so close to each other that they're as close as they can be to being one value without actually being one value, right? This is that whole hairy thing called a limit in math. And it is hairy. It's hard for a reason, because it's a weird idea. But it's an idea that comes from how weird reality is, that we can conceive of two values of a variable, we can conceive of two moments in time being so close to each other that for all intents and purposes, it's one moment in time, except that it isn't actually one moment in time. Because if it really were one moment in time, then there'd be no passage of time and no time to be looking at, right? So when we are talking about that situation, where we're talking about the difference between two values of any variable, like the rise between two heights or the run between two horizontal positions, whatever, if the difference between the two is so small that it's infinitely small, which means it's as close as it can be to zero without actually being zero. And what does that really mean? In science, what does that well, first of all, when it's that, we change our notation from delta to d. And that's all that d means. Like, I did not understand this about calculus for years. I was trying to do, I mean, really, for semesters, I was trying to handle calculus and all these dy, dx's and all this stuff and the definition of the derivative and okay, I'm telling you that it really did pass me. If I feel like I understand this now, it is not because I did it first. What I didn't see is that every time I saw a dy dx, that just meant delta y over delta x, but shrunk to the limit. D is just a replacement for delta. Whenever we write lowercase d and we go to derivatives, well, literally we are just changing from the finite case to the infinitesimal case. And that's a big enough leap to be, whoa, like, what does infinitely small mean? Like, that's why we pause and do all this crazy stuff with limits and delta epsilon proofs and everything in math class, because it is worth pausing if we're going to say something as weird as something, the difference between two values that is so small that it's as close as it can be to making the two values one value, but not quite. Like, that is such a weird thing to say, that all of a sudden we invent all this math to make it make sense. But it's weird enough, and then all the math comes, so then everybody's left completely confused. Like, the idea is weird, and then the math seems really weird. So the two don't help each other, and then it's just. But what I'm saying is, there is meaning to this limit business. This limit business. Okay, this is the clearest I can say it. I should have drawn this bigger. What I just wrote in red is like the key point. If you're ever struggling with what do they mean by a limit? Like, it's as close as it can get to, but it's not there. Like, how not mathy could that be? How not clear is that, right? What I'm saying as a scientist is limit as delta x approaches zero means it's bigger than zero enough to be real and to be there. Like, we're talking about a time interval that actually happened. Like, we were watching the car as it went, the cop was pointing a radar gun at the car for like the millisecond when the car passed by the radar gun. Like, there was a time interval. The car passed by the radar gun. So there's a large enough time interval that we actually are talking about something in reality. But it was such a small time interval that it was too small to register on the measuring instrument of the radar gun. Like, that's literally all we're saying with limit, is big enough to be there, to matter, to be worth measuring, to be worth talking about, to use in our measurements, but too small to measure. Too small to measure. That's what limit means. As a scientist, like, that's a meaningful thing to say. Big enough to be real, too small to measure, right? That's what we're saying with limit. And we care about that very much. We care about it very much because in the end of the day, when the cop pulls you over, I don't mean to say it like that, but like, if you were driving and you got pulled over and the cop says, do you know how fast you were just going in front of that school over there? Do you know how fast you were just going? You cannot say to the cop, well, let's see, I've been in my car for about an hour and I've covered about 30 miles in that hour, like, which might well be true. So I guess on average, I'm going 30 miles an hour. So I don't know what the problem is, officer. Like, no, you can't say that, right? Even if all that's true, like don't say that. And certainly don't quote your physics professor and say it, because that's not what the cop is talking about. The cop doesn't care how fast on average you were going for the last hour. You may well have only covered 30 miles in that hour. So on average, your velocity was 30 miles per hour. But that's not what the cop is saying. The cop is saying right now, a minute ago, you were going super fast. Like, and I don't know, I guess you were parked for 10 minutes before that so that it all averaged out to 30. Like that's not my issue. My issue is how fast were you going right now, right? Instantaneous velocity, the cop wants to know. Well, what is that? That means that, I mean, to say that you were going 85 miles an hour right now, like just now when I pulled you over, you were going 85. That doesn't mean you were traveling for an hour and traveled 85 miles. It means you were traveling for a teeny amount of time that if you had kept going at that rate, if you kept going for an hour, you'd cover 85 miles, right? But we're saying just for this teeny amount of time you were doing that. Well, how teeny? Well, really teeny, to so teeny that it's close to like just a minute, like a moment, like not the separate, not a millisecond, not a half millisecond, not a quarter millisecond, but just like right now is what we think we're talking about. On the other hand, that's impossible to measure. Like, how can you even, like, no, you can't measure now. You can measure now, right? So the limit is so the concept of instantaneous velocity is its average velocity, but taken to the limit as you get as close as you can to no time interval at all, i.e. when you get down to time intervals that are smaller than your measuring scale. That's what we're talking about here. That's what we mean by instantaneous velocity. Okay, so that's what we mean by a derivative. A derivative is a slope in the limiting case where measurement pick it up. That's what we're saying. Therefore, instantaneous velocity. Okay, so again, I'm just putting a new notation for what we said yesterday. But please, for the rest of your life, if you're at all thinking about calculus and limits and stuff, which is worthwhile, dy dx just means delta y over delta x shrunk to the limit. Dy dx is the slope of a curve at a point. Slope of a curve at a point. I know you've heard it a million times and you hear about tangent lines and all that. What's the purpose of it? Because just always remember, we're saying slope of a curve at a point. And that's a paradox because a point cannot have a slope. A point does not go up or down. A point is just a point, right? But what we're talking about is the slope of the curve at the point. We're talking about the rate of the car at that moment. At a moment, a car doesn't actually have a rate. In a photograph, a car doesn't have velocity. But in a movie, a car has velocity, and a movie is made up of lots and lots of frames. So if the motion isn't happening in any one of the frames, and all you get to make a movie is a bunch of frames, if there's no motion in any of the frames, where's the motion? So in each of the frames is a derivative, a rate taken to the limit. That's what instantaneous velocity is. That's what we're saying. So in summary then of all that, so that's the connection between physics and calculus right now is that instantaneous rates of motion from physics are derivatives of position with respect to time from math. Okay, I mean, and that may already be obvious to some of you, but that's all I'm saying. So in summary so far, then, okay. So we have, I know I've written, so we have the average velocity is defined to be that. We have, now I'm going to write this in different order, just so you, instantaneous velocity, we're saying, is the limit of that. And sometimes I use the deltas and sometimes I don't. Like, you know, delta means one thing minus the other, but with t, remember t naught is always 0. So I'm being a little bit casual when I sometimes leave in the deltas and sometimes I don't. But so we have those, and then we're saying now, as I go straight to bring us to the sheet, then accelerate. See, so we said average velocity is displacement over time. Then instantaneous velocity is average velocity taken to the limit. Now we have a concept of instantaneous velocity, then we could say, oh, so acceleration is a change in that. Acceleration, on average, is change in instantaneous velocity per time. I can even now introduce one more quick, I didn't even write this on the first sheet, but just to, if you really get getting where this is going and if you're ready to move on, you'll see that it makes sense. I could just right away say this too, if you're seeing the pattern. right? It is a pattern or it's an analogy or whatever. We have average velocity equals change in position per time. Instantaneous velocity equals the limit of average velocity. Average acceleration is change in instantaneous velocity per time. Instantaneous acceleration is average acceleration taken to the limit. You see, okay? So, or put one final way, and then, oh my God, I have to figure out how, there's reasons to, you get my point. Okay, but hold on, I want to add one more thing to this. What in the name? I just forgot what I was. Oh yeah. Okay, so what I'm saying now, and again, I'm going to fix this board in a second, but it looks like a million new equations, maybe. I'm trying to say that really in principle right now we have four. We have a definition of average velocity and a definition of instantaneous velocity. We have a definition of average acceleration and a definition of instantaneous acceleration. That's what we have so far, just four definitions. We haven't discovered anything. We're like just putting our words together in a way. I mean, hopefully we've discovered a connection between math and physics, but really we're just trying to put our language together. So just one last way of putting the calculus, if it makes sense, I'm saying then ultimately instantaneous velocity is the first derivative of position with respect to time. And if you're just getting comfortable now with derivatives, you might want to write that fully out. Like, it's not good enough to say velocity is the derivative. Velocity is the first derivative of position with respect to time. It's dx dt, rise in position per run in time, taken to the limit. That's what instantaneous velocity is. Therefore, look at the bottom of the sheet, instantaneous acceleration is the rate of change of that. So instantaneous acceleration is the infinitesimal rate of change of position with respect to time, right? So instantaneous acceleration is the second derivative of position with respect to time. Just more notation for the same idea. But this is like where the calculus and the physics connect. Okay, that's still, there's still one more equation I want to give you, like the one that, but is that okay? But actually, yeah, we're going to start relating this now to the fourth homework. I'm going to pull up the fourth homework and change this board. You definitely could have done the fourth homework without all of, I mean, again, this is me just trying to put things in perspective. So you already knew, you'll see. When we do the fourth homework, you don't have to have understood all of this, but even more to the point, to be clear, going on in this class, like this thing here and this thing. Just to be as clear as possible, like the derivative things I'm saying are very important and helpful and will expand our understanding, but you don't plug into them. Like their definitions, it's hard to, you'll see this, but whenever you get a new homework question or a new exam question or something, if you're like, I don't know what equation to use, or you're just trying to like put down an equation that might make sense or something first to get yourself going, I definitely still recommend the two equations that I circled in red. Like that's what your first thoughts really should be. And if whenever you're stuck or you're starting a new problem, start with those. The other two are really useful ideas, but you can't really mechanically use them as directly as the two that I just circled in red. You'll see, for what it's worth. But all right, I think that's, I'm going to turn to homework 4 now. Let me just try to change this. I'm still trying to do this board this way. We'll see. We're going to turn to homework 4. Please take out homework 4. And please stop me if there's any questions at all again. Huh. So now how do I get back? I don't know. My whole experiment to do this in seems to really be, I guess I feel like the world is trying to tell me something. All right, I'm going to go back to landscape mode. I don't know why. No questions. All right, so we're going to homework 4. Excuse me. Okay. But again, if there's any questions at all, okay, so it starts off, sorry, let me just get it. Starts off with this business about Berlin and stuff like that. Oh yeah, all right, so it really is good to draw a picture here first. Yes, number one is a review, but it's important because we really have to start getting positives and negatives straight. Positives and negatives straight. So when it asks for a picture, really, we mean of a coordinate system. It's a really good habit to always, before you start doing anything, just draw a quick diagram to establish for yourself, what do you mean by plus and minus? Like, is plus up or is plus north or is plus south or whatever, because direction matters in physics and we designate it with plus or minus. So let's just say, by picture, I just mean something as simple as this, but I did put on a lot of your homework. Like, you do want to, at least, it's a really important habit, always just right away declare, what do you mean by plus and what do you mean by minus? So here I'm declaring that that north is plus, and I'm even going to say, like, okay, so here's Berlin and here's Rome. And it's 7. All right, so here's my picture. And yes, this is just kind of more. So the total distance for this journey is 700. I mean, there's not much to do this. The difference is the distance is just the spatial interval between the two positions. So the spatial interval is 700 miles. Total displacement, well, if she actually and I should have put this in the diagram. She actually flew from Berlin to Rome. She flew that way. And in my diagram, I said that south is negative. So her total displacement, and I might have accidentally marked this right on a lot of homeworks that is actually wrong. I mean, you know, the displacement is negative 700 miles according to my picture. Okay. Now, could you make a picture where north is negative? Sure, you could. Like, you could make a picture where south is positive. Could you make a decision that south is positive and then say that your answer to B is positive 700? Yes, you could. But you see, your answer is right or wrong only once you define what positive or negative is. This is going back. So what I'm really trying to say is this is important. Is negative 700 like the right answer? According to my picture, it is. If you put positive 100, are you wrong? Well, I say you're wrong unless your picture says you're right. And do you have the right to make a picture differently? Yes. But this is why, if you don't make a picture, I can't assume anything, right? And why must I have a picture, or why must I have a decision about what's positive? Like, I'm literally saying to everybody, okay, I'm literally saying, on the one hand, it's totally your decision. Either answer could be right. You can decide that north is positive. You can decide that south is positive. Literally, you can, because Galileo's principle says the laws of physics will work the same in either direction or in either speed. Sounds obvious, but okay, it's important. If the laws of physics are going to work the same at either direction, then you can call either direction what you want. But if the laws of physics are the same in either direction, either answer we get will be right, but we're still going to get different answers. So we better know what we're talking about, right? Like, just like I can say the Earth is going 65,000 miles an hour past the sun, but that assumes that the sun is going 0. Or I could say that the sun is going 65,000 miles an hour past the Earth, but if I say that, I better say the Earth is going 0. We have to be consistent. Say 59th Street, 14th Street, all that business. So I mean, I don't care. Like, this is just a homework assignment, and I probably gave everybody full credit, like, no matter what, and I hope I did. But just please know, like, this answer to B is negative as long as my picture. Oh, so what I am saying in physics, the trick of physics, really, throughout all of physics, the actual hard part is not the math. The hard part is really understanding that in physics, before you start anything, you always can make a choice. Like there's always a choice that's up to you and gives you freedom, that more than one answer would be acceptable depending on what choice you made. But the catch is you have to make a choice. You have to. The real catch of physics is that it seems like it's your choice. So what the heck? You could just like not, like you're allowed to vote. So you could vote for nobody if you want. It seems like, but it's not that way. It's you're going to make a choice no matter what. So if you don't consciously point out what your choice is, you've still made a choice and all your answers still have to be consistent with that choice. So the key to physics is always knowing we have the right to choose any reference frame we want, but we must know what reference frame we've chosen. Otherwise, things are going to get inconsistent and wrong. Like that's really is the, anyway, that's actually the deal of physics. But so the answer to B is that, okay? So I'm circling my answers, please do. C, the average speed for the journey, okay, is the average speed is, distance over time. So in this case, it's 700 miles over. I know you know this. I know you know how to divide by 4 hours, right? And so the answer to C is average speed equals 175 miles per hour, if I just did that right. And notice, like we were being given in miles and hours, so just give your answer in miles and hours unless asked otherwise. Like you don't have to convert to meters per second or anything. It's just whatever the unit of measurement is. Okay, so that's not, stop me if I'm doing something wrong or confusing, please, for real. But that's C. And then D, according to this whole thing, if V, now we're, if average velocity is displacement per time, and according to my coordinate system, my displacement was negative 700, then my average velocity here is negative 175 miles per hour. And negative is not, and that is correct. Like velocities can and should often be negative, right? It doesn't mean I'm going back in time. It just means I'm going south rather than north, right? So those are my, hello, what is up in there? Sorry. All right, so those are my answers for that, right? Okay, so that's number one. I'm just going to check the chat. Sorry, is any good? Okay, not meant to be interesting, but hopefully clear. Stop me. All right, that's number one. Then I'm going to go on to number two. No, I'm not. Yes, I am. Okay, number two. Oh yeah. Okay, now number two gets into. You see, you can't really talk about average acceleration without talking about instantaneous velocity or vice versa. So that's why it all came up yesterday. But so number two. Now this question is it's not hard, but it's a very good example of some of these new equations and how they mean something, but how you don't exactly use them directly. So right, in principle, this all blah, blah, blah. Okay. Oh, sorry. Okay, so it gives us, so it's asking for instantaneous velocity. And I'm going to get this answer. I'm going to get it by thinking, like not, well, anyway. So what do I know in this problem? What's given to me is that there's some car that travels a total distance, a displacement of 40 miles. And I know that the total time that it travels for is 30 minutes, which you can leave as 30 minutes, or you can put as a half. I'm going to put that as a half hour just because I think that's easier to divide and multiply by, but I don't have to. You could leave it in miles per minute, but I just think a half hour is easier for me to picture than 30 minutes. But either way, it's asking me now, it gives me those two facts. Oh, and it gives me one other fact, one other really important fact. The other fact it gives is that at any given moment, whatever this car is doing is the same as what it did at the beginning. Like, please note this. I'm writing down the three facts of the problem. One of them I'm writing in notation, a notation you might not have considered. what this notation means. Like this means. Right? If ever you see V equals V naught, or anything in physics, if you see A equals A naught, or like something equals something naught, that means that at any single instant, the value of that variable is the same thing as what it was right at the very first instant, like right when we first started measuring. Therefore, it's not changing. It, whatever the variable is constant. So that's our clever way of saying something is constant. We just say the thing equals the thing sub naught. Okay, so these are the three facts. These are the three facts that the problem gave us. They are our three facts. One of them might have sounded more like English and the other sounded like them, but they're all actually facts. And now the question, our question, I'm dragging this out. I know a lot of you got this right, like in one line, but our question here is what is, sorry, actually, in a sense, there's a fourth fact. Our question here is at t equals like 18 point 42, 36, 7, 10 point, like at this. Right, like literally this is the question. And again, I know it's a really easy question in a way. For some, well, I don't know if it is or not, but anybody who got the answer and got it right probably thinks it was like a joke. But if you didn't get it right, there's a reason. Or if you didn't get it at all, there's a reason, because I'm actually asking something a little bit hard here, asking something that we never have asked before. I'm saying you got this car that's going 40 miles, that travels 40 miles in a half hour. I want to know exactly how fast it's going at this weirdo thing of like the 18th minute 0.7 seconds, right? That's a very strange thing to ask. And it does seem like I'd have to plug in a lot of obscure numbers or something. I don't know what to do. I mean, again, I know a lot of you got this right, but let's pretend this is on an exam. I've never seen this question before. All of a sudden, the exam is mentioning like the 18th minute, 0.7 second, like what? So what do I do? Even if I'm not sure what to do or what's going on, my first instinct that I should do here is the first instinct that many of you absolutely did do in the homework, like whether you knew it. What I'm definitely going to do is I'm going to use like the one concept or the one equation or I'm going to write down a definition, because definitions are never wrong. Even if I don't know what to do with it yet, I know definitions are right. So sure, I'm going to write down something like this, as many of you did. Or maybe some of you just skipped straight to the numbers, but I would caution you not to. Like I write down, okay, average velocity equals displacement over time, right? And then I plug into, I'm like, oh, cool. I have the displacement. I have the time, like, assuming this thing starts at position 0, I'm like, oh, average velocity equals displacement per time. And I've got displacement and I've got time, right? So I'm going to plug them in. And what time do I put in? I'm not putting in 18.7. I'm putting in 0.5. Like this thing took a half hour. Like, I don't know how many miles it traveled at 18.7 minutes. So I'm not plugging in 18.7, right? Like what I know is that in a half hour, this thing traveled 40 miles, or right? So I'm plugging those in, as many of you did, and then dividing. And so I'm going to get, okay, 80 miles per hour. Now, if you're still with me, please stay with me. Here's where, like, the question is that the answer or whatever? Yes and no. Okay, yes and no. Anybody who thinks the answer to this ultimate question on the homework, if you think the ultimate answer to the question, the thing that you should box and say is right and that you'll get full credit for, if you think the answer is 80 miles per hour, you are correct. The final answer will be 80 miles per hour. But I also want to say, I don't know that yet. What I'm looking at here right now is that the average velocity for this car is 80 miles per hour, right? And that is what we should always start our analysis with whenever we're solving any problem. We should always think about averages first, because as I was trying to say on Monday, averages are things that you can picture and observe and measure for an interval. Like the thing went 80 miles, we measured it. The thing took a half hour, we measured that. So we divide one by the other and we say, aha, on average, for this entire half hour, on average, this car was going 80 miles an hour. That's what we can know right away. That's the first thing you always do on an exam or whatever in life. You compute an average first because you can, and we did. But now I have to recognize, and I might not know, like I might be doing this just because I know how to. I might not know how to get to the end of the problem yet. I might not even be sure I understand the question of the question. But I know that this works and is right, and I did it. So now what do I know at this moment? What I know is on average, that car was traveling 80 miles per hour. Like I don't yet know anything about any given moment. This right now is like me saying to the cop, well, I've been traveling for a half hour and I know that I've been in my car since I left home a half hour ago and my home is 40 miles away. So yeah, I know that on average for the last half hour, I've been traveling 80 miles an hour. But the cop is interested in how fast I was going at a certain moment, in this case, like the 18.7th minute, right? So there's no way to leap from this to that. Like you can't just plug into that limit equation or something like because limits don't work that way. There's no way to leap from 80, from my average. Like this is my average. There's no way, but what I'm saying is, what I'm trying to make very explicit here, and as always, this is meant to be not a super hard question. It's meant to, not have too many details to think about or something so that you can picture the actual kind of hard thing I'm saying, which is that V with a bar over it and V without a bar over it are very different. One is approximate and average, but easy to work with. The other is exact and perfect and right and what we care about, but harder to work with, impossible to measure, only possible to know if you think it through analytically with math and things like calculus, like, right? Honestly, so I'm just trying to remind you for one last time, right, that you cannot know how fast a car is going in a photograph. It doesn't mean it's not going in a, right? You can't know how fast a car is going at a moment in time, because literally at a moment in time, a car is not going anywhere. It's like 0 over 0. What you can know is if you picture some moment of time that you've extracted or excerpted or interpolated in your mind from some larger movie. Like if there's a movie of a car driving down the highway, and then you're looking through that movie and you freeze the movie on one frame, so you know that frame is taken from a larger context, then you can talk about what must be happening in that frame. Just like one point doesn't have a slope, but if you look at if you pick a point from some larger curve and you zoom out and you look at the larger curve and you see, oh, when that point occurred, the curve was on its way up or was on its way down. Like that's what we're saying here. We're saying you can only infer an instantaneous quantity from some knowledge of the larger whole, but you have to have large. So what's the knowledge that we have here? Here, like, so we don't know our answer for V. We know our answer for V bar. If you just write down like V bar equals 80, you're saying something right, but you haven't finished answering the question yet, right? How can we use the one other fact that I haven't used yet, but I have to explicitly use it. I have to realize, that at any given moment, V is whatever it first was, which means at any given moment, V is whatever it is on average, because it's never changed. In other words, if I say to you, I mean, this is really important. I'm saying here. I'm saying, I'm making a big deal out of something that I'm sure some people think is obvious, but I'm saying when you divide 40 by a half and you get 80, What you've gotten is the average velocity. You can call that the instantaneous velocity at the 18th moment only because you've been told that the thing never changed its velocity at all, right? If this thing were accelerating at all at this moment, I can't tell you. I don't know at this moment how fast it was going at the 18th minute. I only know that. So basically this question right now comes down to saying, like, say you know that there's a whole wall that I painted, okay? And you know two things. One, I painted the leftmost corner red. Two, I painted the whole wall the same color. What color is the wall over here at the top rightmost corner? You'd say red, because only because I already told you the whole wall was the same color, and I gave you one other piece of the wall and said it was red. So you're like, well, then the whole thing is red. That's what's going on here, right? We don't automatically know what color a piece of a wall is unless we're given some knowledge about the whole rest of the thing. That's how derivatives work. You don't know rate at a point unless you think of 2 points around that point and start bringing them closer and closer together and capture that point. All right, I'm over talking this, I'm sure, but so the answer here to this one is 80 miles an hour. But if it were on an exam, honestly, I would have to see this step, some like this last step that I put in red, some version of it. Could be in English, but you'd have to show. All right, I'm going to shut up. I'm going to go on to the next one. I know that's a lot. All right, I'm just going to keep going. Please stop me again if there's anything, but I'm just going to keep going because I know this is also like ponderous. So the next question. I think now we get into average acceleration, right? So now we start doing some examples with units and numbers, right? So now I think it talks about my Toyota. That's a real example. I really did have a 1975 Toyota. Green hatchback, 4 on the floor. It was a great car. Where I just lost, sorry. Okay, right, so here's the definition, written another, hopefully you see how the way the definition is written here is consistent with the way I'm writing in the notes. I mean, okay, but anyway, so 3A. Okay, so we have this Toyota Corolla. All right, so what do we know here? We know that there's a time span. We measured something for 2 minutes. And what did we find out? We know that at the beginning of those 2 minutes, the car was at rest. And we know that at the end of those 2 minutes, the final instantaneous velocity was this, right? This is what is given here. And now notice, now the units are a little bit funky. The units are intentionally given, they're intentionally given like sort of realistically in ways that hopefully we can relate to. They're not meant to be confusing. They're meant to be not confusing. Like cars, we tend to measure their speeds in miles per hour, but small time intervals, we tend to measure in minutes. So here's our facts, right? Notice what's given here are in 2 different instantaneous velocities, a first one and a second one. You could call these V1 and V2 if you like. You could even call them V initial, V final, like depending on what textbook or what web resource you're getting this out of, like these all mean the same thing. You could say it however you want, but it just means 2 distinct, but just know none of these has a bar over it. They're all instantaneous velocities. So another way to put it, if you want to organize things in your mind, like initial velocity, final velocity, or velocity 1, velocity 2, or velocity naught, V0 and V, all of those are all examples of instantaneous velocity. Like that's one category. Instantaneous velocities includes initial velocity, final velocity, any velocity at any moment is what we mean by instantaneous. And that's what we're being given here. So now we're being asked, what's the average acceleration? Okay, I'm just going to apply the definition. This is just a plugin, so I'm going to apply the definition. Our new equation is this definition of average acceleration. Okay, so it went from okay, so just as you might think, the answer to this now let's pause on this for a second. I know math-wise, this is just arithmetic. You're dividing 60 by 2 and getting 30. Like that part is hopefully not meant to intimidate anybody. And I think a lot of people got it right. Like, yeah, the short this is what I would like your homework to look like, more or less like this, like showing the work and all that. But I understand that this exercise, most of us probably just, if we got it right, we did like 60 divided by 2, we got 30, and that's our answer. But let's look at what this means for, and it's right. I mean, that's good. But let's look at what this answer means for a second. Like, this is not incorrect. This doesn't look like science, maybe. It looks like we still have to do a unit conversion or something. And maybe that is why there's part B. Like maybe this will be a little bit cleaner if we get the units consistent. But even if it's like dirty right now, it's not wrong. And it actually does mean something that I can relate to, which is this. What this is saying, this answer, 30 miles per hour per minute. That is a legitimate acceleration. Oh, wait, you could write it a number of different ways. You like, hold on. I'll go to the next page. Hold on a second. I'm saying, like if I'm walking, okay. What this is, sorry, what this is, I want to, we're not talking about accelerations. Accelerations are changes in velocity per time. Velocity already is change in position per time. So what we're talking about here, whether you want to think about it as derivatives, whether you want to think in calculus terms or not, either way, what we are really talking about here is distances, displacements per time again. Like it's very real and important and like not a mistake that there are 2 units of time in our answer here. In this case, one of them happens to be hours, the other minutes. In the next case, we'll see they're both going to be the same. Either way, there's 2 units of time. And that means we're dividing by a fraction, which really always throws everybody off. It throws everybody off, even people that are used to it, because when you divide by a fraction, like something flips, so you never know if it's getting smaller or bigger. So let's just be as clear as we can be. What we're saying about this Toyota here, are like all of these that I just wrote on the board are all interchangeable. They're all different ways of saying, they're all equal. They're all different ways of saying the same thing. I'm saying that what my car does is every minute it gains 30 miles per hour of speed, right? Like, that's what I'm saying. Every minute, it's in other words, velocity is like every minute the car gains distance. Every minute that goes, if my car has velocity, that means every minute of time that passes by, my car advances through space. That's if it has velocity. Now we're going to the next level. We're going to the second derivative and saying, yeah, well, if it has acceleration, which it might not have, like if it's not just driving, but if you're pressing on the accelerator, then we're saying that every moment of time that passes by, not only is the car advancing through space, but it's actually advancing through speed numbers, right? It's like not just is the car moving, but the speedometer needle is moving, which it wouldn't do if we were driving on cruise control, right? Like, so in this case, this car, every minute, the car is not just getting 30 miles farther than it was before. Every minute, this car is getting 30 miles per hour faster. And it's not illegal that we're saying, so we're saying every minute, it gets 30 miles per hour faster. We're using 2 different time intervals, but they're not messing each other up. They're both being invoked, right? I think that makes sense. I can actually picture that. Yeah, I'm literally saying that if this car kept doing that, then a minute later it'd be going 30 miles an hour. A minute after that, it'd be going 60 miles an hour. A minute after that, it's going 90 miles an hour. Like that's what it means, right? But you might think it's inconsistent or confusing to have hours and minutes in there. So the next so even though that's valid, another valid thing to do in science is to convert the units and make them consistent. So in next part, I guess it's B. Where'd it go? I just lost. Oh, yeah. In part B, right now it asks, what about miles per second per second? Okay. Oh, does it miles? Miles. Now, no, I'm writing it like that from the. Now, this is just a unit conversion. This is a unit conversion problem. Oh, and I am looking at the time. I see we have 15 minutes, 13 minutes. This is a unit conversion. Two things about unit conversion. First of all, everybody hates them. I know. I mean, it's like, why? Like half the reason people don't even make it through science is because unit conversions are so annoying and boring. I get that. But the other problem with unit conversions, besides being seemingly boring and annoying, is that they're also actually always harder than they should be, right? Or they often, like if they were just super easy, then they wouldn't be as boring. But they can be complicated, especially when the unit conversion involves any kind of dividing. When there's something in the denominator, that tends to throw people off. And now we got not only something in the denominator, but we got something like two of them. So it is worth pausing again. Let me just show you on this back. Remember that miles per hour per minute, like remember, like this, miles per hour per minute means the same thing as this, miles per hour per minute. But that means the same thing as miles per hour per, like if you're dividing by dividing, that means both the hours and the minutes go down to the denominator. I don't know how to say it better than that, really, other than that. Just always remember that 1/3 divided by 4, right? 1/3 divided by 4 is not the same thing as 1/3 divided by 1/4. You know that 1/3 divided by 1/4 is actually the same thing as 1/3 times 4. Maybe I'm saying this too fast, but right, when you divide by a fraction, then you multiply by the reciprocal. But that means if you divide by a regular number, you don't do that. Like, so don't double flip accidentally. In other words, miles per hour, miles divided by hour, divided by minute means that both the hours and the minutes are down there in the denominator. It's the best, I can't really say it better than that. This. So that means what we're looking for here, right? They're both in the denominator there. So we're looking for a situation now where what we want 2 units. We still are going to have 2 units of time in the denominator, but we actually just want them to be the same here just for consistencies. So I am going to do a unit conversion, but I got to be careful, right? So I'll do it once just to show everybody the way I do unit conversions. Bear with, but I'll say, and also because like a lot of people did get this wrong in the homework, to be honest. It is just a computation, but one does have to be careful. But here's and this will be the last thing we do today. I apologize. What am I going to say? Oh, what I think is that everybody knows at some level that there's 60 seconds in a minute and that there's 60 minutes in an hour. So somehow I think everybody knows we're going to be like dealing with 60s. The thing that starts to throw people off is whether we're multiplying by 60 or dividing by 60. The one thing I would say from the outset is try to maintain perspective. Like we're going to try, we know how many miles per hour this thing gains every minute. If I ask myself, how many is it going to gain every second? That better be a lot smaller, right? If it gains a certain amount in a minute, Well, a second is less time than that. It's not going to have as much time to gain. So presumably it's going to gain even less. And also what it's gaining is miles per hour. Like, but if I'm asking how many miles per minute is it going to gain each, well, whatever speed I'm doing in miles per hour, like if I'm going 60 miles per hour, that means I'm only doing a lot less than that every minute. I'm doing only like 1 mile every minute. What I'm really trying to say here, I'm going to do this carefully. It will probably bore some people, but I think it will help some people. Also, you just might want to see my way because I don't know, it might be helpful. But know from the outset, I'm going to convert 30 miles per hour per minute into miles per second. I better get a much smaller number. What I'm really trying to say is, especially if this is going to be the last thing we do today, whatever, before you do a unit conversion, before you let it get you stressy, or before you think you're all macho about it, like make a prediction in your mind. Are you hoping to get a smaller number or a bigger number? We better get a smaller number here because we're going from miles per hour per minute to miles per second per second. So if I don't get a much smaller number, I've done something wrong. Okay, so I'm saying that. Now, what am I going to do? I'm going to say what we have right now. We have, and again, this is the last thing we'll do today, but and literally I'm going to do this once now, but hopefully it helped, but we're never going to do it again because in principle, we all hate doing it. I mean, we're going to do unit conversions all the time, but just not like together as a group. So I'm saying this is how I do unit conversions. What I always do, I always, even if I think I know what's going on in advance, the way I do unit conversions, especially when they look thorny, is every step I do, I always just multiply. Because the big question is, do you multiply or divide? Do you multiply? Like, that's what always confuses people. I know what the number is, but should I multiply or divide? Here's what I do. I always multiply. I always multiply by what I call the well-chosen one. It's very biblical. I multiply by one always, right? Because whenever you multiply something by one, you don't change it. So I'm always multiplying by one, which really means in secret terms, I'm always multiplying by something over itself. Like I know 7 divided by 7 is 1. 4 divided by 4 is 1. X divided by X is 1. So what I always do to do a unit conversion is I multiply by something over itself. And the only thought I put in, the only choice I ever make in my unit conversions is, what do I put some, like I don't ask, am I multiplying or dividing? I'm always multiplying. But when I decide whether to put something over something or the other way around, I look to see what units have to cancel. Well, you'll see what I'm saying right here. So I go like this. 30 miles, I'm going to multiply by a well-chosen one. Well, what do I mean by that? Well, I mean, for example, one of these minutes needs to be changed into seconds. I know there's 60 seconds in a minute, right? So now the whole question is, what should I do with that fact? What I do is I multiply by, I know I know that 1 minute is the same as 60 seconds, right? 1 minute equals 60 seconds. Therefore, by writing 1 minute over 60 seconds, it's like writing X over X or Y over Y. It's writing 1. So I haven't messed anything up. The only thing is, the real point is, so I knew to write 1 minute and I knew that equals 60 seconds. I knew I was going to use that unit conversion. But as to whether I multiply or divide, what I do is I know I'm going to multiply, but how I decide whether to put the minute up top or the minute up bottom is I know that I want to cancel out minutes and be left with seconds. So what I always do is multiply by a fraction, but I decide how to write the fraction by looking at what units have to cancel out and what have to stay. Like that's what I do. So I've got this so far, right? And then I'm going to do it again. Like, so minutes will cancel and I'll have miles per hour per second, but I'm not there yet because I still have to get rid of those other hours. So I do it again and I go, well, there's 1 hour. 1 hour, I want to cancel out those hours. So I put an hour on top. There's 1 hour is the same as 60 minutes. I'm going to run out of room here, right? So that's a good thing. So now I see that my hours are going to cancel. And of course, I didn't give myself enough room. And So now I've got miles on the top, which is good. I've got seconds on the bottom, which is a start, but I also have minutes. So I got to do this one more time, get rid of one more thing of minutes. So I do, again, 1 minute, I want to get rid of those, is the same as 60 seconds. So the minutes cross out. This is, and again, this always work. Unit conversion, I mean, because it's actually really powerful. That's why we do, but just always just multiply by 1 and just arrange your fractions so that the proper units cancel out. So now I look at it. I haven't done the numbers yet, but now I'm looking, I'm like, oh, I got miles on the top. I got seconds on the bottom and seconds on the bottom. So I'm good to go. So now I can just like literally do the math. So, I mean, the computation, and we have like 4 minutes, and it's perfect. So I have like 30 on the top, and I have like 72,000. I think I better check in a second, but I think I have this on the bottom. Is that because 6 times 6 is 36, and 36 times 6? No, that's completely wrong. Sorry. 36 times 6. I should know that. I'm sorry. 36 times 6 is 216. All right. So yeah, sorry. Now I'm losing my mind. Oh, what? What did I just do? Sorry. Oh, I'm sorry. I'm totally. Oh, no. That's right. I'm sorry. Yeah. Okay. So you have this on the thing. Right. And this is where we're going to stop. And I'm going to rewrite. This is where we're going to stop, but I should have given myself more room because I really want you to see this answer clearly. So I'm going to write on the next page. I'm saying the answer is this. I'm saying it's approximate because we did chop. I'm chopping off digits as I look on my calculator. I'm chopping off digits, so it's approximate. That doesn't mean it's wrong. It means it's approximate. But I get this. And what units do I get? I get miles. I get seconds times seconds on the bottom. And that's called, and this is where we're stopping. Oops, but sure, this final answer is like a second times a second is a second squared. I mean, x times x is called x squared in math and physics. So we call this answer 1.39 times 10 to the negative 4 miles per second squared. And indeed, in physics, all accelerations will be measured in units of all accelerations. Whenever I use square brackets, that means units. All accelerations have units of displacement times time squared. The squared just means that time is coming into the denominator twice. It means it's like everything we just said, like meters per second squared really just means meters per second. It's all it means. It doesn't mean we're actually squaring time or doing anything weird or psychedelic like that. We're just saying that every acceleration has to be a rate of change of velocity per time. So a rate of change of position per time. That's where the squared, so meters per squared is just like saying meters per second, or meters per minute per hour, whatever. That's all it is. And that's our answer. And we totally all have to go. I have to go to the next class. You have to go. So wait, let me just, I'm good if you guys are good. If you just say goodbye. I mean, I'll stay for a second if there's any question. I'll stay till you all go, but goodbye. And once you, please say goodbye, and I love you all. And okay, so goodbye. Sorry. Goodbye. Thank you. Bye.
Thank you. Have a good day.
Thank you. Have a good day. Great. Thank you. Bye, Noelia. Bye, Camilla. Bye, 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 Michelle. Bye, Amarani. Bye, Jennifer. Bye, Agia. Bye, Luna. Bye, Dorina. Bye, Yasmin. Bye, Whiteboard. Bye, Nikai. Or no, that's your question. Okay, wait. Okay. Bye. Thank you. Bye, Yasmin. Thank you. Bye, and bye, Luna. Bye, Jennifer. Bye, Agia. Bye, Nikaya. You guys are good? You guys are good? Goodbye.